Perfect. Great. So thanks a lot for the organizers to inviting me and organizing this kind of last minute. So Marcin spent last 40 minutes telling you about hands. So now it's time to switch gears a little bit and talk about legs. So in particular, this talk will be about the environment that we released a few months ago for the purpose of improving research in RL. And before I start, I just wanted to mention that it's like a big effort, and there were many people involved from Google Brain in Zurich and also from Google Brain in Amsterdam. So why do we even need environments for reinforcement learning? So I hope Marcin convinced you that RL recently had a lot of success, like in robotics, in applications like data center cooling. People are starting using it for self-driving cars. But the main problem with RL in real world is like extremely hard to scale and deal with. So, you know, robots break. You cannot buy 10,000 of them. It may be expensive to set up, or maybe if you have a self-driving car, you don't want it to hit the wall multiple times to learn something. So this is why people often use video games to experiment. They are easy to use, they are cheap, you can scale them using just machines, and they provide like a very nice test bed to try very different research ideas. So probably you heard of those recent advances that Marcin mentioned, like Dota, StarCraft, or Computer Go. And those environments, those games that people are using comes with different trade-offs. So on one hand, there's a bunch of environments that are like very easy, like Pendulum Task or maybe Atari, that people already know how to solve to superhuman level very quickly. On the other end of the spectrum, we have things like StarCraft or Dota that actually requires like a huge research team, maybe 100,000 CPU and TPU pod to even be able to do something very simple. There's also a bunch of very specific environments to some given problem, like, you know, Mujoko can be used for robotics. Maybe there are some environments like chess or Go that assume that you're given the model of the world. Or maybe some of the environments are deterministic, like Atari. So for our research, we're looking for something that's kind of like, it's still generic, but it's in between. So it's definitely should be more complex than Atari, should provide more complex state, more complex dynamics, ideally stochastics. It's easy to modify, easy to do multi-agent and multiplayer experiments. Yet at the same time, we didn't want to spend hundreds of thousands of CPUs. We wanted like average like research labs to be able to use it. So this is why a few months ago, we created a Google Research Football environment, which looks like this. So as you can see, it's similar to popular video games such as FIFA or Pro Evolution Soccer. Here, the goal of the agent is to learn how to pass, tackle, like dribble, and basically how to figure out a strategy and score against the opposing team. So we focus mostly on high-level strategy, not really the low-level control, kind of like in a DeepMind soccer environment. Okay, just maybe to make it clear. So like the goal is to develop RL algorithms because of some properties. Like if you like to work on model-based algorithms, that could be a nice test, but if you like to work on multi-agent, that could be a nice bet. Like really beating the built-in agent, it's not our goal, unlike Dota, where it really was the challenge that people wanted to beat the bot. Here the goal is to use this environment to progress RL. Okay, so to summarize, like high-level overview of Google Research Football is it consists of three main components. The first is the football engine, which is like optimized simulation that has some specific RL features that I will be talking about. It's a set of football benchmarks, which are reference tasks on a full game 11 versus 11 that are aimed for people to have some number that they compare to when they create a new method. We also have Football Academy, which is a set of smaller tasks of progressing complexity, such as, for example, doing the corner kick or maybe just learning how to pass the ball. And the idea here is we wanted to have something that people can very quickly test if something is not totally broken, like unit tests for RL. Okay, so let's start with the football engine. So the football engine that we used for Google Research Football is based on open source simulation called Gameplay Football. It's a game written in C++. We highly optimize it. We added some Python bindings. For example, it follows the OpenAI Gym interface. It has also some additional feature useful for model-based RL, but in general, we are fully compatible. It has a bunch of very useful features, for example, you can train without rendering, which is very useful for RL. Or you can do some kind of easy multiplayer. So, as I mentioned in the engine, the standard setup is 11 versus 11 players. On each side, we support all standard events that you would expect of a football game, like kickoffs, offsides, getting cards, kicking corners, etc. The players have different statistics. They can get tired over time. And actually, we measure the length of the game in terms of number of actions of the agent. So we allow to perform one action every 100 milliseconds, and we give 3,000 steps for an episode, which gives 5 minutes of real-time game. And everything, I will mention it also later, but everything here is very easily customizable. So if you would like to change some parameters, maybe you want shorter games, or maybe you want different players, maybe I don't know, 5 versus 7, or maybe you want to give a reward for passing, it's super easy to do. Also because the game is open source. All right, so the standard mode of the game, if you would like just to try it out of the box, it's similar to FIFA, right? So, I mean, you just control one player, you can challenge the built-in AI, which is based on some rules. And we provide 3 default difficulty levels. Also, in the standard setup, all your teammates on a team are also controlled by the built-in AI. So, you control the player with the ball, the others are controlled by something that follows some reasonable rules, like, try to get closer to the opponent if you don't have a ball, or try to follow you when you have the ball, etc. But as I mentioned, it's very easy to activate this multi-agent mode, in which you can send, actions to all players at the same time. So this is actually very interesting because in many modern reinforcement learning systems, it's actually very important to handle the multi-agent situations. Like, you can think of self-driving cars. I mean, there is a car, but there are also other actors in the scene. So you want to develop methods that are robust to it. So this can be actually very useful for trying different methods. Another feature that is working out of the box in environment, and it's very cool, is that it really supports multiplayer. So in environments such as Atari, even if you have some opponents, they are not really controlled by agent. They are part of the environment. Here, you can really train the model and then play against the same model. Like, you can play against it yourself as a developer just to see how easily it would be to beat. You can play agent versus agent, which allows, for example, the self-play method. And there is also an option to play on an external game server that we provide that we'll be talking about later. Regarding the action set, so we use 20 discrete actions. So agent can choose different, basically the standard move directions, different ways of passing and kicking the ball. It can sprint, dribble. One interesting information is, like, if you recall how it works in games like FIFA, you usually have a special button to switch the player. Actually, we couldn't do this here because when we added action to switch the player, the usual outcome was the policy was learning just to switch away and don't deal with playing with the opponent. So, I mean, you can still add actually this action. I mean, the game is open source and this action exists. It's just not added in the default action set. The rewards. So in environments, I mean, I guess you already guessed it. There is like a very standard reward. If you score a goal, you get +1. If you don't score, you get, I mean, if you lose a goal, you get -1. And ideally, we would just have this reward, but it can be sometimes very challenging. Like if you're playing, let's say, hard opponent, it may be that the scoring event is extremely rare. And because of that, we also introduced this like a helper reward shaping, which gives agents some additional reward for moving closer to the goal. I mean, as I said, it's like nothing stops you from adding like new reward. I mean, if you believe that, I know, you have to pass at least 5 times before scoring, and you want to give like additional reward for passing, I mean, you can very easily try it. But this is something like what we provide out of the box. Also, the environment supports natively 4 different types of representations that it can return. So the one is just raw pixels. So like what you would observe in like if you played the game. Also, the raw pixels are used in Atari, for example. It can also return the floats. So like exact location of the players in your team, exact location of the players in the opponent's team, location of the ball, etc. So this is kind of interface that people are using like in Dota or in StarCraft. We also observed that just playing from the minimap works actually very well. And especially if we stack several minimaps over time, then the performance of the standard MLP controller is not that much worse than LSTM1. And so what is very nice is that for all of those 3 representations, they don't require any GPU. So even if you have like a bunch of strong CPU machines, you can already do a lot of training. Which brings me to this point, which is the performance. So as I said, we spent like really lots of time optimizing this game engine. And after all of those optimization on a like commodity hexa-core machine, we are able to obtain 140 million steps per day, which makes it actually very nice because yeah, you don't need this GPU cluster or TPU cluster and thousands of CPUs, but you can very quickly try many different ideas. Right, so let me talk a little bit about benchmarks in the academy. So I'm not going to get into exact details here, but I just wanted to mention that those benchmarks is this, like the standard task. It's like, I mean, what you would expect of a football game. 11 versus 11, all rules, like action every 100 milliseconds, length of the game 3,000 steps. We allow 3 difficulty levels. And we provide the results on the standard RL algorithms such as IMPALA, PPO, and DQN. In addition to this, we also have this Football Academy, which, as I mentioned, is like a set of tasks of progressing complexity. So just to give you an idea, what can it be? Here, you have a scenario that you have to learn how to run, because if you don't run, those bad guys will come to you and take the ball from you. Here, this is the counter-attack scenario, which is like 4 versus 2, I believe, and you have to learn how to score in this. Here you need to learn how to pass, and here is the corner. So all of those scenarios were just created with a like Python configuration. So nothing stops you from creating your own very quickly. And just wanted to mention that some of them are like really, really easy. Like shooting to empty goal when you're close to it, you can train in like several minutes. But some of the tasks actually can get much harder, like corner or like running to and scoring with the goalkeeper. They're actually much harder than this. All right. So when you are training RL systems, probably you already noticed that it can get very tricky depending on how you shape reward and how the environments behave. So we had one actually very interesting example, like what happens when we use the standard scoring reward, but the agent actually realizes that it's worse than opponent. So I'm not sure how it's visible here, but like, okay. Okay, so basically what's happening here is that the agent on the left realizes it's much worse than the agent on the right. So, and what it's doing, instead of doing the free kick by the goalkeeper figure out that the only winning move for them is not to play. So it's like running around on the field and waiting for the time to pass. So, so they can actually lose only 1-0 and not like 10-0 because, I mean, makes sense, right? Yeah, but like, you know, they just, I mean, that was kind of thing that was in the original game, but like nobody ever noticed it because, I mean, people wouldn't do this. But, I mean, AI figured it out. And actually, the next example is even more interesting. So we were testing Academy, and we were looking at the scenario that there is only one goalkeeper in the opponent's team, and we have someone with the ball attacking. So how would you score a goal in this situation? Like, normally humans, I guess, okay, I would run towards the goal, I will try to maybe tackle the goalkeeper, maybe try to avoid it, maybe shoot from the distance. But because the environment is stochastic, this may fail, right? I mean, the pass maybe not, I mean, maybe the goalkeeper will manage to catch the ball or something. So actually, what the agent figured out is the best strategy would be just to kick the ball to out. Because there's only one player in the opponent's team, it has to throw in the ball. Now, now the goal became empty, right? Smart. So those are like, some people would call them emerging behaviors. Some people would call them bugs in the environment. Yeah, so actually now this can be also controlled as a part of the config. And this is something that's not mentioned as one of the components because Football League is the thing that we are going to release most likely this week. So if you go to this web page, you will see a football server on which you can play the Google Research Football. There's like a bunch of different tracks. The idea is that you can train your model locally. You can just connect to the server. Basically, you switch one line. Instead of creating environment, you create remote environment. So that's the only difference. And you can challenge other researcher. You can challenge our bots. And yeah, possibly that might evolve even in a bigger tournament. Yeah, so that's how it looks. There are some like ELO ratings. All the games, I mean, I don't have it on the slide, but there are like also like some recent games. There are like the videos are sent to YouTube, so like if you beat some of the better models, you can share it directly. And you have a bunch of. So currently we have 2 tracks. One is just like a debugging track, which is one-on-one, like goalkeeper versus goalkeeper. This is really debugging. The other is the standard 11 versus 11 game. So. Yeah, I mean, if you're looking for an interesting research project, I would totally recommend trying your bot here. And yeah, how to get started. So all the code is publicly available at this GitHub location. We are quite responsive to issues and emails. So like, if you would like, I mean, if you notice that something doesn't work, definitely let us know. Yeah, we will try to help. And this is just like a snippet how simple this could be. So basically you can, like after you install, which I mean takes around 2 minutes, you can just import the environment and then you follow like the standard OpenAI setup. So I mean you pick the action, you call nth step. I mean that's it. I mean it's really not complex. And if you are wondering what could you do with this, I thought there are like two research directions that are particularly interesting. So one of them is like really multiplayer. So, there is this problem in self-play that if you train one agent versus the other agent, and then you train this agent versus some other one, it's not necessarily transitive. So we did this small experiment that we train agent A versus built-in AI. Okay, so it's winning. Then we trained agent B versus A, and the agent B was also winning. Now we tested B versus built-in AI, and it sucks, right? So one of very interesting research questions like how you deal with this problem, how you design the training so it's not really forgetting. One approach is to just train against the mixture of the previous agents, but maybe there are better methods. The other direction that is super interesting, in my opinion, is multi-agent. So, okay, so here, does it play? Okay, so here basically we consider a scenario in which, okay, play. Perfect. All right, so here we consider, we did like a small experiment in which we compare single and multi-agents. So in the first video that you will see, the agent is controlling only the active player with the ball, and the teammates are, oops, nope. Okay, one more time. Right, so in this scenario, the agent controlled the player with the ball, and the teammates are controlled by built-in AI. So standard like FIFA setup. So, the game is stochastic, so the best policy that the agent is able to learn scores in around like 76 or 77%. But then, when we switch the agent to control all of the players, okay, one more time. Okay, so when we switch the agent to control multiple players, it's actually able to figure out a better policy, a policy that is able to score in 97% of the cases. So this is actually super interesting, and especially if you do the training on full 11 versus 11, it might be able to discover some very interesting strategies that we never thought of. So yeah, I think generally it's very cool. So I advise you to give it a shot, or at least to play on the server, because it should be very fun. And yeah, this concludes the 20 minutes. Thank you very much, and we are waiting for the questions.